Calculating moments. So a moment is the turning effect of a force around a pivot point, like this point here, and we have the magnitude of this force and its direction given by the arrow. So together the direction and the magnitude create a vector. Now in the formula it's the magnitude that we want, and it's multiplied by the perpendicular distance from the pivot point to the force. And this line here, this is the shortest line that you can draw between this point and this line. Any other line drawn between this point, the pivot point, and the force line is longer. See, this line now is longer, this one's longer. The shortest line between the force line here and the pivot point will be the one that creates this right angle here, the perpendicular distance between the pivot and the force. And the units are in newtons from the force times meters from the distance, Newton meters. So in this example we can see that the distance here, 2 meters, it's not the perpendicular distance between the pivot point here and the force line here. At that angle 60 degrees, it should be 90 degrees. So to draw the perpendicular distance, I need this line that creates a right angle right there on the force line. So now this distance is the perpendicular distance, and given by trigonometry it's 2 sine 60. 2 sine 60 degrees, and we're using the sine function because we have the hypotenuse and we want the opposite side to the angle, so it's going to be the sine function. And then we have to state the direction of the moment, so it's either clockwise or anti-clockwise. And in this example, this force line here, it's pointing downwards, and relative to this pivot point it's going to create an anti-clockwise motion around this pivot point. Have a look at the previous video on moments to better understand clockwise and anti-clockwise moments. So example 1, we want the moment around the point P, that's our pivot point, and looking at the direction of this arrow for the force relative to the pivot point, we're going to get clockwise motion in this direction. So formula, put in the numbers, 10 Newton meters clockwise. You must state the direction. In this example, the perpendicular distance between the force and the pivot point is 0. So it's force times perpendicular distance, 0 Newton meters. Example 3. Now this is not the perpendicular distance that we need to calculate the moment. So we have a choice. So we know that the distance between the pivot point and the force should create a right angle on the actual force line. So there's the right angle and it's on the force line, so this one's correct. In this diagram, here's a right angle, but it's not here where it should be on the force line. So this is incorrect, that's wrong. We're going to stick with this. So 2 times sine 60 will give the opposite side. So then we have the force, 8 newtons, times the perpendicular distance, so this one here in red, 2 sine 60, and 8 root 3 Newton meters, that's the exact value of the moment, or 13.9 Newton meters. And we can see the force, if we follow the direction of the arrow and we go around the pivot point, it's anti-clockwise. Example 4. So once again, the 5 meters here is not the perpendicular distance, so I need to draw a line between my pivot point and this force line, and again it's going to be the shortest distance between the pivot point and the force line, and it's here. And it's always in such a way where you get a right angle triangle, where the right angle there will be on the force line. So we have a 40 degree angle in here. This is 180 minus 140. So 5 times sine 40 along here. 5 sine 40 degrees. So that's the perpendicular distance that we're looking for. Okay, so we have 10 the force times the perpendicular distance, 5 sine 40, and if we simplify, 32 Newton meters, and the direction, well, here's the pivot point and the force is in this direction, and if you continue along around the pivot point, it's clockwise. Example 5, and once again from the pivot point to the force line, this is not the perpendicular distance here. So if I try and draw a perpendicular distance, it looks a bit unusual to begin with. So what I should really do is if I just keep the direction of the arrow the same, but just move everything over a little bit like this, now I can draw in my right angle triangle like this, and the right angle needs to be in contact with the force line there in the diagram. So then the force 10 newtons times the perpendicular distance, which is 2 sine 60 here, and we have 17.3 Newton meters. Again, relative to this pivot point, if I follow this force around the pivot point, it's in a clockwise direction. For practice, try these questions.